So let's try to make sense of this data then. The simulation, these reactions that we're looking at between the iron and thiocyanate system and also the cobalt system. How can we make sense of this by looking at the concentrations? Well, here's how we should do it. So I wrote the equilibrium expression for this A plus BC in equilibrium with AB plus C. And so the first thing that we're going to look at, this is from the simulation, is the first scenario when I added some of A, when I increased the amount of A particles. So when I did that, let's think about this equilibrium constant. When I increased, I got up arrows. Then I'm going to show this. Ooh, easy there, Tiger. When I increased the concentration of A, what we observed was that BC went down, 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 down. And as a result, AB went up and C went up, like so. That seems interesting. Here's how we can think of this. It may not make sense right now, but if you think of it from a mathematical standpoint, this KEQ right here is constant. Changing the concentration of reactants or products does not alter the equilibrium constant. Therefore, when I change the concentration, it must be what it was originally. So we could have calculated this equilibrium constant. We could have done that by taking the concentration of the products over the concentration of the reactants. And if you remember from the simulation, it was about 60 products and 40 reactants. And so on top, I could take 40 times 40, or other way around, 40 products, AB, and 40 Cs, and 60 As, and 60 BCs. So 40 times 40 over 60 times 60, and it's going to give you a number that's less than 1 because there's more reactants than there are products. Let's just say, hypothetically, that value is 0.5. Well, that KEQ value, if it's 0.5, it has to stay 0.5 even when I add more A particles. So to compensate for that, if my denominator is going to get bigger, my numerator also needs to get better to compensate for that increase in the denominator to maintain a 0.5 equilibrium constant. Additionally, BC would have to come down a little bit to help lower and decrease how much that denominator is actually going up. And so therefore, that's why the equilibrium stays the way it is shifts the way it does, is to maintain that constant equilibrium constant. So this is how we often talk about this, is that when we increase something like A, what that does is it shifts away from the increase. So it shifts to the right. In other words, it shifts away from the increase. Well, what happens if I decrease? Well, let's look down here. So for instance, in the example that I gave, you decreased the amount of C particles. So when you decrease that, what we saw was an increase in AB, but that also led to a decrease in A particles and also a decrease in B particles. Well, why is that? Well, when you decrease the amount of C, you got to maintain that constant equilibrium value of 0.5-ish. That means your numerator is getting smaller. Well, in order to do that, the denominator would also have to get smaller, but that AB is going to increase a little bit to help with the numerator not have to decrease so much. And so therefore, the way that we talk about this is when we decrease something, that means that it's going to shift towards that. So when we decrease the concentration, it's going to shift towards the decrease, away from the increase. And that's how Le Chatelier's principle can be summarized when talking about concentration changes.